Welcome. Today, we delve into an industrial mystery at the heart of World War II's greatest logistical achievement, the rapid mass production of Liberty ships. But behind the triumph lies a shocking enigma. How did ships built in just days suddenly begin to break apart without warning? Imagine a newly launched Liberty ship fracturing in Portland, Oregon, with no storm, no enemy fire, just brittle steel tearing itself apart. Simultaneously, reports of over 2,500 structural cracks flooded the naval archives between 1943 and 1944. How could ships, constructed with cutting-edge welding techniques borrowed from automotive science, fail so catastrophically despite using what was considered the best steel available? Could the secret to these deadly fractures lie hidden in overlooked details that would challenge everything we thought we knew about manufacturing safety? The answers threaten to unravel a monumental lie, one buried deep in the industrial processes of wartime America. Are these failures mere accidents? Or is there a far darker truth behind the designs and decisions? If we peel back the layers of this story, we'll see how tiny residual stresses and welding sequences turned into fatal flaws, forcing an industry to rethink the very foundations of shipbuilding. Ready to uncover what truly caused these catastrophic failures and how frontline workers' insights led to a groundbreaking revolution? Then let's begin. In the early days of the 20th century, the world had witnessed extraordinary leaps in technology and industry, but nothing seemed as groundbreaking or as urgent as the effort to build a fleet capable of turning the tide of a global conflict that had already reshaped nations and devastated continents. When America entered the Second World War, the need for shipping was not merely critical, it was absolute. The Atlantic was a battleground of commerce, hope, fear, and death. To meet this relentless demand, a new maritime miracle was born, the Liberty ship. A vessel designed not just for utility, but as a symbol of American industrial prowess and wartime resolve. These ships, born out of necessity, were to be the backbone of Allied logistics, ferrying troops, supplies, raw materials, and hope across perilous oceans and hostile waters. Their significance was undeniable. They were America's answer to a decimated merchant fleet, a rapid response vessel born from the chaos and urgency of global conflict. And in the haze of war, they were shown to the world as a testament to American ingenuity, fast, efficient, and seemingly invincible. But beneath this shining facade of achievement, darkness began to emerge. The first cracks of doubt appeared on a cold January day in the year of 1943 in the bustling shipyards of Portland, Oregon. The SS Schenectady, a freshly assembled Liberty, was nearing completion, its hull gleaming in the winter sunlight. Yet, just as inspectors prepared to launch her into the roaring Pacific, creaking sounds, sharp and unforgiving, heralded the beginning of catastrophe. Standing on the dock, surrounded by the muffled hum of machinery and the faint smell of freshly poured steel, the inspectors noticed something strange. Fundamental fractures in the ship's structure, cracks that defied all expectations. No enemy attack, no storm, no sabotage, just an inexplicable failure that challenged every assumption about these industrial miracles. How could steel that had been rigorously tested, designed around proven principles, fracture so suddenly, so inexplicably? A cluster of overextended welds? A hidden flaw lurking in the assembly line? The reports did not end with the Schenectady. Similar failures soon followed. Ships such as the John P. Gaines, the Manhattan, and countless others. Between the years of 1943 and 1944, more than 2,500 reports flooded in, describing ships with creeping cracks, bolts loosened, hulls buckling beneath their own weight. An alarming pattern was emerging, one that threatened to undermine the entire wartime maritime effort. To understand the magnitude of this crisis, one must grasp the revolutionary process behind Liberty ship construction. These vessels were not built like traditional ships, crafted over long months or even years by skilled artisans. No, these ships were born of the desperate need for speed. The construction time was slashed from months to a matter of weeks, sometimes barely over 42 days. This was not just quick, it was revolutionary. Workers on assembly lines moved like conveyor belts, fabricating sections from pre-made components. Modern techniques, welding instead of riveting, transformed the shipyard floor into a kind of industrial ballet. Prefabricated sections arrived, fitting together seamlessly, or so it seemed. This flow of parts, borrowed from the automotive industry, was hailed as an unprecedented industrial miracle. The propaganda was relentless. Images of ships built in days, ships pushed out faster than ever before, ships symbolizing American resilience and technological supremacy. One vessel, the SS Robert E. Perry, entered the record books, completed in an astonishing 4 days and 15 hours. The message was clear: America was winning the war in the shipyards. Yet, beneath this tide of triumph, a disturbing undercurrent lurked. The very techniques that promised speed and efficiency would soon reveal their dark side. Cracks appeared not just as mere surface flaws or superficial blemishes, but as deep, propagating fractures that threatened to tear the ships apart from within. This was no ordinary problem of materials aging or fatigue. Evidence began to accumulate. Evidence that pointed to an even more troubling possibility. The failure might be embedded in the design and manufacturing process itself. Industry experts, naval architects, and metallurgists pored over reports, analysis, and samples. They examined the steel used, looked for signs of weakness, impurities, unrecognized flaws. Yet, despite the exhaustive tests, the explanations remained elusive. Steel that seemed perfect at first glance occasionally fractured under minimal stress. Welds that appeared sound held secrets within their microscopic structure. Secrets that could unravel the very integrity of the hull. The central enigma deepened, a paradox that was impossible to ignore. Why, despite employing advanced techniques, utilizing high-quality materials, and adhering to engineering standards, were these ships suddenly breaking apart? What mechanism could possibly cause such catastrophic fractures in vessels that should have withstood the harsh demands of war? For all their speed and size, the Liberty ships seemed fragile, vulnerable to forces that should have been accounted for, yet somehow were overlooked. The evidence, unyielding, irrefutable, points to a failure not just of materials, but of understanding. An oversight in the very principles of manufacturing, a flaw buried beneath layers of assumptions and industrial optimism. What was the true cause behind these seemingly inexplicable fractures? Was it a failure of steel, a flaw in welding, or perhaps an unrecognized stress in the assembly process itself? Investigations revealed that despite efforts to control every variable, something fundamental had gone wrong, something that challenged the entire foundation of shipbuilding and manufacturing safety. It was as if the very process that promised to deliver expedited results had unknowingly introduced a hidden menace, corrupting the integrity of steel at the microscopic level or weakening the welds with unseen flaws. The questions echoed louder with each new failure. Could a factory-made vessel, assembled in record time, truly be as durable as a traditionally built ship? Or was speed and volume all that mattered, regardless of the hidden cost? And so, the investigation grew more urgent. Beneath the surface of victory and innovation lurked a crisis, an intricate puzzle with pieces scattered across steel mills, assembly lines, and inspection rooms. Each failure peeled back another layer, exposing the fragility disguised behind technological progress. The facts amassed, reports, metallurgical studies, eyewitness accounts, painted a picture of a system under siege. The Navy's best minds faced an agonizing dilemma. Should they continue to push for rapid production at the risk of catastrophic failure, or halt to uncover a truth that could redefine everything they knew about building ships? The answers to this mounting crisis lay hidden in overlooked details, details that challenged the core assumptions of a burgeoning industrial age. These details, seemingly minor or insignificant, held the key to understanding why these mighty ships, which had so vividly symbolized American resilience, were turning into floating time bombs. The device that would ultimately unearth the root of the failures was not a new invention, but a re-evaluation of centuries of engineering wisdom, an attempt to see what had been missed, something that would forever alter the understanding of manufacturing safety and the fragility lurking within the engines of modernization. This was a story rooted in the depths of industrial ambition and human error, a story that still resounded with urgency. Because the truth was not just about ships or steel. It was about trust, about the delicate balance between speed and safety, and about the unseen vulnerabilities hidden within the very fabric of the war effort. In seeking answers, investigators would have to confront not only the technical mysteries, but also the broader implications for an entire industry that fought to prove that even the greatest technological advances could hide silent, deadly flaws. And lurking behind the curtain of progress was the undeniable realization. Sometimes, progress itself demands a heavy toll, unless the underlying failures are unearthed and understood before it is too late. In the vast, sprawling shipyards along the coast, where steel giants took shape amidst the clamor of rivets and the roar of massive machinery, a quiet revolution was simmering, unnoticed by the bustling facades of progress. Among the thousands of workers shaping cold, steaming steel was a woman named Bessie Hamill. A seasoned welder working at Kaiser's Richmond shipyard, she knew her craft intimately. She had seen the toll of rushed assembly firsthand, and her keen eye observed something unsettling, not just within the steel she welded, but lurking insidiously in the patterns of her work. It was late in the afternoon when she first began noticing it. The ship's hull, freshly welded and cooled, looked pristine from afar, smooth, intact, promising salvation on the seas. But close up, she observed a subtle warping, a slight distortion at the edges, where welds had been made. The pattern was unmistakable, a sequence of welding starting from the edges and working inward, a standard procedure dictated time and again by the shipyard's protocols and for decades considered the safest way to build these monoliths of steel. Yet, she sensed that this method might be causing harm. She saw the steel curve and twist under her scrutiny, as if tension threaded its way through the very fabric of the metal. Driven by an innate curiosity and a sense of duty, Bessie decided to conduct an informal test, her own investigation into whether the standard welding sequence might be creating more problems than it solved. Clad in her gear, with an array of steels and welding tools carefully arranged, she methodically tested alternative sequences. Her approach was simple, yet revolutionary. Instead of starting from the edges, she began welding from the central sections, gradually working outwards. The results were startling. The steel constrained in this manner showed far less distortion, far fewer internal stresses. The warps shrank, the joints remained straighter. But would her superiors accept her findings? Of course not. Her concerns, deemed unproven and inconvenient, were dismissed with dismissive nods, the kind that closing ranks often issue when faced with unwelcome truths. Undeterred, Bessie pressed on. She documented her experiments, compiled samples, and showed her supervisors the clear contrast. Steel affected by her modified welding sequence was noticeably less stressed, less prone to cracking. Yet, her warnings fell on deaf ears in the boardrooms. They had their routines, their schedules. The integrity of the ships was secondary to efficiency, to meeting deadlines that paid the bills. But the facts, relentless and irrefutable, could not be silenced. Professor Analysis confirmed her suspicions. Stress tests demonstrated the alarming reality. Conventionally welded steel panels trapped internal tensile stresses that soared beyond 30,000 pounds per square inch, an incendiary recipe for disaster in the right conditions. Bessie's alternative sequences, by contrast, kept these residual stresses comfortably below 12,000 pounds per square inch. And it was no small factor. These internal tensions, invisible yet potent, were ready to ignite doom when the ships faced the brutal cold of the Atlantic waters. In the icy depths, steel lost its strength, its ductility. Residual stresses acted as catalysts, opening cracks that silently formed within the hull, waiting for the moment they could propagate, a moment that often came suddenly and catastrophically. The new freight of tragedy was insidious, lying in wait beneath the steel surface, ready to fracture without warning. The flaws weren't solely in the steel's composition or the improbable shape of the hull. They lay deeper, embedded in the very process of assembly. Yes, the ship's design had its flaws, sharp corners gleaming like flaws in the white noise of productivity, squared-off corners that trapped stress like insidious time bombs. But those were not, as some believed, the root cause of collapse. The true catalyst was hidden in the welding sequence, a factor overlooked, dismissed, neglected, and the residual stresses it engendered. Brittle fracture, the swift, cold killer of steel, was propagated not by poor steel, but by internal tensions that set the stage for failure long before the steel ever met the brunt of the Atlantic storm. Could it be, then, that the ships betrayed their builders not because of inferior materials or flawed design, but because of something almost invisible yet infinitely potent? The unseen residual stresses etched into their bones? The facts, the evidence, the analysis, their weight undeniable, pointed unambiguously to this conclusion. The tragedy was not fated by the steel itself, but by the processes that forged it. This discovery pierced through the fog of conventional wisdom, challenging everything that had been accepted about ship construction. The idea that a simple change in welding sequence could have saved countless lives, prevented catastrophic loss, was revolutionary. The very foundations of mass production standards, built on routines, protocols, and assumptions, now faced scrutiny. What other practices, similarly overlooked and underestimated, might threaten the safety of these floating giants? The implications ignited a flame of reckoning among engineers and safety officials alike. The realization struck with mounting force. The path to true structural integrity lay not merely in superior materials or more rigorous design, but in understanding and controlling the hidden internal stresses embedded within the welds. It demanded a radical rethink of how ships were built, how safety was understood, and how oversight was exercised at every level. If residual stresses could be as destructive as the cold Atlantic itself, then the entire fabric of mass shipbuilding had to be re-examined from its roots, from the very sequences that welded steel into the leviathans we entrusted with our lives. In that moment of recognition, a new chapter in maritime safety was born. Instead of accepting the status quo, engineers and workers now faced the challenge of mastering the unseen forces lurking beneath the surface, transforming the very art of shipbuilding into a knowledge driven by vigilance, insight, and respect for the complex realities of steel and stress. The silent, deadly role of welding sequences and residual stresses would never again be dismissed as trivial. It was, unmistakably, a matter of life and death. In the sterile, humming confines of the industrial shipyard's testing laboratory, a quiet revolution was quietly taking shape, one that would challenge centuries of maritime engineering doctrine and upend the very way steel ships were built. It began with a question, one that haunted every engineer's mind in that era of war and relentless progress. How could it be that the steel, our strongest material, could turn against us so suddenly and so violently when faced with the icy depths of the North Atlantic? The answer lay in a subtle, almost invisible force, a phenomenon buried deep within the molecular fabric of the metal itself. Kaiser, a figure of commanding authority yet marked by a sharp scientific curiosity, had reacted sharply to the insights of a sharp-minded metallurgist named Hamel. The theories Hamel presented, supported by meticulous analysis, suggested that the sequence of welding, the very process of fusing steel, could be manipulated to fundamentally alter the stress profile within the ship's hull. It was a daring notion at the time. To test it, Kaiser authorized an audacious plan: to take full sections of hull steel, painstakingly reconstruct them under laboratory conditions, and subject them to the revolutionary welding protocols Hamel proposed. Picture the scene: long days and even longer nights. The workshop was filled with the smell of heated steel, the sharp clang of welding torches, and the steady hum of measuring instruments. Steel plates, once part of enormous vessel hulls, laid out like the bones of some ancient creature, were subjected to a series of experiments that would challenge conventional wisdom. The goal was clear: to measure and compare internal tensions, to understand how different welding sequences affected the residual stress within the material. The results were startling. Conventional welds, those made quickly without regard for stress relief, exhibited internal tensile stresses soaring beyond 30,000 pounds per square inch. Such internal tensions, hidden from plain sight but detectable through sensitive measurements, signaled impending disaster. But the experiments with stress-relieved welding sequences told a different story. When Hamel's procedures were implemented, the steel subjected to carefully controlled heating and cooling cycles, internal tension plummeted below 12,000 psi. The difference was not subtle but revolutionary. A dramatic reduction in internal stress meant the steel could withstand more. It was not just about strength anymore. It was about resilience, the ability to absorb shocks and resist fractures. The composition of the steel remained unchanged. Carbon and alloy elements were the same, but the way it was welded dramatically altered its physical behavior. This shift in methodology was rooted in a fundamental physical principle. Steel, like all metals, responds dynamically to temperature. When heated, it becomes ductile, flexible. When cooled, it hardens. But improper sequencing during cooling, such as rapid, uneven welds, creates residual tensile stresses. These tensions are embedded within the steel's structure, essentially locked in imperfections of frustration and strain. As time passes, these residual stresses become the seeds of catastrophe, especially under the brutal conditions of the North Atlantic's freezing waters. The icy environment exacerbates the problem. Steel that is ductile at higher temperatures becomes brittle as temperature drops. It loses its elasticity, taking on a new guise, one that is vulnerable to crack initiation at the very points where stresses concentrate. And here was the crux of the matter. The sinking of ships like the SS Schenectady aligned precisely with this scientific understanding. When the ship met the cold, the steel's brittleness was camouflaged and masked by a false sense of strength. But the residual stresses, already embedded during initial welding, did not disappear. Instead, they lurked, waiting for their moment. When the vessel succumbed to the icy depths, the fracture pattern revealed a tale of internal tension and cold brittleness intertwined. The breaking point was not a random failure. It was a predictable, science-driven event. The steel, compromised by residual tensile stress, fractured abruptly, like glass struck at a weak point. Rapidly, catastrophically, with devastating finality. Unlike riveted ships, which relied on discrete joints, each rivet a tiny point of vulnerability, welded hulls were seamless. They appeared, on the surface, like monolithic monoliths of metal. But this very continuity was a double-edged sword. Crack propagation had no natural barrier. A crack initiated at one point could race across the seam without interruption, unhurried and unstoppable. The continuous welds, when compromised by residual stress and low temperatures, became highways for fracture rather than barriers against it. The difference in failures between riveted, patchy joints and continuous, welded seams became starkly evident in the wreckage and fields of debris that told the story of maritime catastrophe in days long past. The question that haunted engineers and scientists alike was profound. How could they intervene in this chain of cause and effect? How to prevent these brittle fractures from transforming a ship's voyage into a one-way journey to disaster? The answer came slowly but surely. Modifying welding sequences and ensuring the steel's stress profile was within safe limits would diminish the internal tensions that turned steel brittle when chilled. Implementing stress relief heat treatments, sequencing welds to avoid concentration points, and controlling cooling rates all contributed to this new paradigm. A paradigm where the science of materials took center stage, where knowledge replaced assumptions and guesses. This shift was not merely about improving shipbuilding. It was a revolutionary reimagining of how industry, beyond the docks and shipyards, approached structural integrity. The significance extended far beyond the icy seas. It laid the groundwork for safer infrastructure, more resilient bridges, towering skyscrapers, and even spacefaring vessels. The insights that emerged from this research and experimentation challenged existing dogmas, forging a new path rooted in scientific understanding and meticulous engineering practice. In essence, this was a turning point, a moment when science and industry aligned, transforming what once was a craft based on tradition into a discipline governed by innovation and evidence. As these revelations took hold, they heralded a new era. The engineering community began to understand that the strength of steel was not just chemical composition or thickness, but also its internal stress profile and how it was processed. Every weld, every heat treatment, every sequence of cooling, each step wielded the power to make or break a vessel's destiny. The knowledge gained was revolutionary, offering the possibility of ships that could brave the coldest, most unforgiving environments without succumbing to hidden, destructive forces within their very bones. In this story of scientific discovery and industrial transformation, the core question persisted. How can we understand and manipulate the invisible forces within the materials we rely on? The answer, as demonstrated through Hamill's insights and Kaiser's bold decisions, was clear. It was the mastery of process, the understanding of material behavior under extreme conditions, that would ultimately prevent brittle fracture propagation in cold marine environments. It was a revelation that would ripple through industry and history, changing the face of shipbuilding forever. And so, in these silent, steel giants that crossed the icy wastes, lay the testament of human ingenuity, proof that knowledge, carefully wielded, can forge resilience out of vulnerability and turn the tide against nature's most unforgiving forces. This was the dawn of a new era, one built not solely on raw strength, but on understanding, precision, and the relentless pursuit of safety amidst the brutal cold and relentless depths. In the relentless rush of wartime production, every ship launched into the churning waters of the Atlantic or the treacherous Pacific represented more than just a vessel. It symbolized a fragile hope for victory, a lifeline for troops and supplies, a testament to industrial might. Yet beneath the steel surfaces of these colossal vessels lay a hidden menace, an Achilles heel rooted not solely in design flaws or material deficiencies, but in the very process by which they were built and tested. It is within this crucible of urgency, innovation, and painstaking craftsmanship that the transformative efforts of Kaiser emerge, a story of scientific rigor, relentless correction, and profound engineering insight. By the beginning of 1944, the American shipbuilding effort faced a sobering reality. The initial design and manufacturing protocols, subjected to the monumental pressures of war, had produced ships that, despite their impressive dimensions and formidable appearance, bore a hidden vulnerability. Catastrophic brittle fractures, sudden and devastating, had begun to appear in a small but alarming subset of vessels, particularly in colder waters where low temperatures sharply reduced the ductility of the steel. These fractures no longer seemed random. Evidence pointed to a critical flaw in the very material that formed the backbone of the ships. The question loomed large. Could these failures be eradicated? Or would the relentless advance of war demand sacrifices of precision and safety? The response to this crisis, spearheaded by the visionary engineer and industrial leader Henry Kaiser, was nothing short of revolutionary. Recognizing that mere incremental improvements would not suffice, Kaiser ordered a decisive halt, a pause in the relentless drumbeat of construction. The ships, once hurried along assembly lines, now faced scrutiny. Each weld, each rivet, each piece of steel was an object of analysis. The focus shifted dramatically. No longer could speed be prioritized over safety. Instead, a comprehensive overhaul was implemented, founded on next-generation welding procedures, structural modifications, and an innovative approach to steel alloy design crafted explicitly to meet the brutal demands of low-temperature environments. The first stern measures involved retooling the entire welding process. Thousands of welders, once trained in rapid, mass-production techniques, faced intensive retraining. The new protocols emphasized sequencing, thermal management, and stress relief, transforming what had been ad hoc procedures into scientific, repeatable processes. Welds that once risked introducing residual stresses became carefully controlled sequences, each heat cycle and cooling period deliberate and precise. Welds were no longer just joining two metals. They became carefully orchestrated steps in reducing internal stresses that might later manifest as brittle fractures. No detail was too small. Every temperature spike, every sequence of passes was scrutinized, measured, and standardized. But steel, the very bones of these ships, also required revolutionary adjustments. Steel is not simply a matter of pouring molten metal into molds. It is a complex dance of chemistry, heat, and mechanical properties. Kaiser's team embarked on extensive research to redefine steel specifications. The existing steel, known for its brittleness at low temperatures, was systematically analyzed, its chemistry dissected under microscopes that revealed microscopic flaws and composition shortcomings. The result was an upgraded alloy, deliberately engineered to withstand the icy grip of winter seas. Carbon content was reduced to mitigate brittleness, while manganese presence was increased to improve strength and ductility. Most notably, small additions of nickel, precisely 0.25%, were incorporated. Nickel, long known for its toughness enhancement, especially at low temperatures, became a vital ingredient in this new steel blend. The impact of these alloy modifications was profound. Laboratory tests and field trials demonstrated that the so-called killed steel, a term denoting a fully deoxidized, carefully controlled alloy, lowered the ductile brittle transition temperature dramatically. Previously, steel would become brittle at around 40 degrees Celsius, forcing ships to become vulnerable in icy seas. Now, thanks to thermal and chemical treatments, this transition shifted closer to 5 degrees Celsius, almost a freezing point of water, rendering the steel resilient even in the most unforgiving cold. This was not mere incremental progress. This was a paradigm shift. The evidence was irrefutable, confirmed through exhaustive testing, physical analysis, and real-world observation. The old vulnerabilities, once inscribed in the very makeup of the steel, were effectively eliminated. What made this overhaul truly extraordinary was not solely the changes to materials and procedures, but the systemic reorganization of the entire shipbuilding process. Modular prefabrication became the norm. Smaller, manageable sections constructed with controlled welding sequences, then assembled with precision. Gone were the days of massive, continuous welds prone to residual stresses and microcracking. These prefabricated units could be prepared in controlled environments, their welding completed under carefully monitored thermal protocols. When integrated into the ship's structure, they formed a robust, stress-optimized hull, one that could withstand the immense pressures of the ocean's coldest depths without succumbing to brittle failure. In tandem with these technological advancements, new assembly methods emerged. Parallel construction of modules, rapid phased integration, and innovative logistical strategies slashed construction times from months to mere days in some cases. The immense industrial machinery of war became a symphony of precision engineering. Each hull, each component, meticulously crafted, tested, and assembled. The process was no longer chaos but controlled, deliberate, scientific. Kaiser's vision had transformed shipbuilding from a hurried response to a battlefield necessity into a disciplined craft rooted in stress analysis, metallurgical science, and engineering excellence. Underlying all these layers of innovation was a simple yet profound question. Could these meticulous, science-driven redesigns truly eradicate the flaws that had caused the earlier disastrous failures? Could engineering precision override the chaos of wartime urgency? The evidence gathered over subsequent months showed a decisive yes. The new procedures, materials, and methodologies drastically reduced the incidence of failures at low temperatures. Ships that previously risked brittle fractures in icy waters now sailed safely, their steel resilient and their welds stress-free. The fusion of science and industry had forged a new standard, one where safety and speed could coexist, where engineering mastery could meet the brutal demands of war. This transformation wasn't just about fixing a flaw. It marked a fundamental change in the philosophy of shipbuilding. No longer was it a race against time alone, but a pursuit of engineering perfection, a discipline rooted in the understanding of materials, stress management, and precise manufacturing. It was a shift from improvisation to innovation, from intuition to analysis. The story of this overhaul underscores one of the most remarkable triumphs of industrial science, turning human ingenuity into an armor against nature's brutality. It reshaped not only the ships that crossed the oceans, but also the very principles underpinning modern engineering. At the crossroads of necessity and ingenuity, Kaiser's approach demonstrated that with enough understanding, discipline, and meticulous craftsmanship, even the most formidable natural adversities could be overcome. This comprehensive overhaul, these deliberate, science-backed interventions, these years of relentless effort, changed the course of maritime history. It proved that detailed attention to the microscopic details could have macroscopic consequences. It proved that true safety arises not from haste, but from understanding. As these ships braved the frozen waters, their steel unyielding, their welds resilient, they stood as silent witnesses to the triumph of human ingenuity over nature's harshest tests, a testament that the science of stress management, applied precisely, could truly save ships, lives, and, ultimately, the outcome of a global conflict that demanded nothing less than excellence. In the relentless march of war, where every second counted and the fate of nations hung in delicate balance, the shipyards of America faced perhaps their greatest challenge. Could they revolutionize an age-old craft, shipbuilding, so profoundly that the vessels would not only be faster to produce, but also stronger, more resilient, capable of withstanding the most brutal confrontations the war could offer? By early 1944, amidst the cacophony of alarms, the roar of machinery, and the hurried footsteps echoing through the sprawling complexes, a transformation was quietly taking place. The Kaiser yards, known for their efficiency and innovation, had embraced a revolutionary approach. It was no longer merely about welding steel plates together. No, the process had evolved into something far more precise, more scientific, a meticulous art of modular construction, stress relief, and sequenced welding. These principles flowed from the latest insights in materials science and engineering, where understanding the behavior of steel under stress, temperature shifts, and fatigue became foundational. The days of slow, laborious shipbuilding, with haphazard welds and inconsistent quality, were giving way to a new era. The factories hummed with purpose, each section of steel pre-assembled, tested, stress-relieved, then seamlessly integrated. The future of wartime shipbuilding was no longer a gamble but a calculated, methodical process designed to produce not just ships, but superior ships, vessels built to endure. Among these innovations, emerging from the chaos of wartime production, was the legendary SS Benjamin Warner, the world's first victory ship. Its keel was laid with hurried urgency, yet its construction was anything but haphazard. In a feat of engineering audacity, this cargo carrier was built from keel to launch in a miraculous span of just over 5 days. Imagine the scene. Massive cranes hoisted prefabricated sections into place. Welding torches flared like lightning in the night, and the air was thick with the smell of molten steel and the relentless clangor of metal meeting metal. But what set this extraordinary vessel apart was not merely speed. Beneath the surface, the ship's structure embodied the principles of stress relief and modular integrity. The implication was clear: speed alone was meaningless if it compromised strength. By employing advanced inspection protocols, magnetic particles tracing potential cracks, ultrasonic waves echoing through steel, X-ray scans revealing hidden flaws, the Kaiser yards guaranteed that each victory ship surpassed the standards of safety and durability. This commitment to quality translated into tangible wartime triumphs. Victory ships, like the SS Juan de Fuca, emerged from battle scars more resilient than their predecessors. Their robust design included features like crack arresters and redundant load paths, allowing them to absorb damage that would have sunk older ships. These vessels did not succumb easily. They weathered mine strikes, artillery hits, and the most punishing ocean storms. Their structural redundancy enabled them to operate with minor hull breaches, engines humming tirelessly in the face of adversity. Unlike the Liberty ships, a symbolic backbone of the merchant fleet, victory ships demonstrated a new paradigm. Resilience was no longer an aspiration. It was built into their very DNA. And resilience was most crucial in the freezing channels of the North Atlantic and Arctic, where the cold turned steel brittle and the sea's fury threatened to snap ships like fragile glass. Victory ships, thanks to an unprecedented overhaul of steel composition, incorporating low-temperature toughness, faced these icy waters with confidence. They proved capable of withstanding temperatures that would shatter lesser vessels, ensuring critical supplies reached besieged allies, maintaining the logistical lifelines that sustained the war effort. The evidence was irrefutable. Over 531 victory ships operated flawlessly during the conflict, their safety record far superior to that of the older Liberty class. But could this revolutionary approach, the rapid, modular, stress-relieved construction, truly surmount the traditional limitations of shipbuilding? Could it transform a factory assembly line into a fortress of safety and speed? The answer, confirmed through relentless analysis, was an unequivocal yes. The entire process challenged centuries of craftsmanship rooted in slow, handcrafted traditions. It demanded a new mindset, a harmony between engineering science and industrial execution. Success required meticulous planning, rigorous inspection, and innovative techniques that turned once weak points into strengths. The results: ships built faster but stronger, capable of operating under the most punishing conditions, withstanding damage, and maintaining operational integrity that was previously unimaginable. Victory ships demonstrated that engineering excellence, when synchronized with manufacturing precision, could turn inherent structural weaknesses into steadfast strengths. Their design was not merely a response to wartime necessity, but a glimpse into a future where technology and industry would forge vessels, and perhaps other marvels, capable of defying nature's fiercest onslaughts. They offer a lesson as enduring as the steel from which they were built, that true resilience arises when innovation molds the processes, materials, and standards into a unified force, one that surpasses what tradition alone could ever achieve, leaving a legacy that would influence shipbuilding and engineering for decades to come. In the crucible of global conflict, the victorious integration of science, technology, and industry proved that the impossible is only delayed understanding, waiting patiently for those bold enough to redefine the very essence of strength and speed. In the vast, thunderous world of wartime shipbuilding, amidst the cacophony of rivets, hammers, and shifting steel, there emerges a story of unexpected brilliance, one that would ripple through decades of engineering, shaping the very standards that safeguard lives today. It is the story of a woman named Bessie Hamill, a frontline worker whose keen eyes and practical insight did not just solve a singular problem, but ignited a revolution in the understanding of stress and resilience in metal structures. To grasp her profound impact, one must first step back into the chaos of the 40s, where necessity forced innovation and desperation demanded precision. During the Second World War, the United States embarked on an unprecedented industrial mobilization. Victory ships, long, narrow giants of steel, became the arteries of Allied logistics, ferrying troops, supplies, and hope across treacherous oceans. These vessels were built rapidly, under intense pressure, with a relentless focus on speed and output. Every rivet, every weld, had to be perfect, or so it was believed. Yet, beneath their mighty exteriors, these ships had a hidden vulnerability, residual stresses lurking silently within their metal structure, risks that could, under certain conditions, lead to catastrophic failure. It was an engineer's nightmare, an invisible force threatening the integrity of these crucial vessels. In this high-pressure environment, a frontline worker named Bessie Hamill, a welder by trade, noticed something unusual. As she worked late into the night, her hands steady despite fatigue, she observed cracks appearing in welds that, by all conventional standards, were flawless. It was an irritating paradox. Welds that met all accepted standards still failed prematurely. Her experience told her there was more beneath the surface, more than just quality of the welds themselves. She felt something deeper, an accumulation of unseen stresses, a residual tension left behind after the welding process. Her keen observation, born from countless hours at the rigging's edge, revealed a phenomenon that the engineers had overlooked. The sequencing of stress relief in welded joints was crucial to their durability. But her insights, initially dismissed by supervisors engrossed in meeting deadlines, would prove to be vital. They lay dormant in the dusty archives of wartime experimentation until post-war engineers began to analyze failure patterns more closely. The adage of strength at all costs gave way to a more nuanced understanding: the importance of stress relief sequencing and residual stress management. As the nation transitioned from wartime urgency to peacetime rebuilding, these lessons seeped into the fabric of American engineering. They found their way into the American Welding Society's standards, initially as a footnote, then progressively as doctrine. The year of 1947 marked a turning point, when the first official guidelines incorporated principles that Hamill had inadvertently kindled, principles that would influence far beyond the shipyards. The significance of her discovery resonated loudly across industries that depended on welded steel. Offshore oil platforms rising from icy Alaskan waters, pipeline systems spanning harsh terrains, and critical components within nuclear reactors all became arenas where the residual stress theory held sway. Consider the offshore platforms of the 1980s, icons of modern engineering battles against the unpredictable sea. many failures traced back to the unchecked residual stresses embedded during their construction. The same occurred with the infamous Piper Alpha platform explosion, a tragedy that claimed dozens of lives. Investigators uncovered that improper stress management had played a role, and the lessons from wartime shipbuilding, lessons Hamill helped highlight, became pivotal in their analysis and subsequent reforms. Yet, the story doesn't end with retrospective lessons. Today's welding industry is profoundly modernized, employing computational models that simulate thermal behaviors and residual stresses with astonishing precision. These are the descendants of Hamill's initial observations, an intricate dance of thermodynamics, structural analysis, and material science. Engineers now wield software capable of predicting where stress concentrations may develop, guiding them to optimize welding sequences, cooling rates, and even material selection. The complexity of contemporary engineering, be it constructing vast nuclear vessels or floating wind farms, rests on this foundation. The once silent residual stresses are now mapped, understood, and controlled, all because of a frontline worker's instinctive, meticulous observation. This seismic shift also redefined how the engineering community viewed manufacturing processes. They are no longer mere steps in production, but inseparable from the structural performance of final products. The perspective expanded from designing with materials alone to designing how those materials are fabricated, welded, and treated. An integrative approach emerged, one that bridges the gap between design and manufacture, ensuring safety and resilience are woven into every phase. At the heart of this evolution lies the story of Bessie Hamill herself, a shining example of frontline ingenuity. Her instinctive attention to the cracks and stresses in welds was born from her daily labor, from the sweat and soot of the shipyard. Her insight was unrecognized in her time, overshadowed by the rush of war and the hierarchy of engineering. Yet, her contribution is embedded deep within the core of modern safety practices, an unassuming heroine whose practical wisdom influenced protocols, standards, and the safety of countless lives. Her legacy is invisible to many, yet it permeates industrial practices worldwide. In the rigorous safety checks, the meticulous stress analysis, the resilient structures that stand firm against nature and time, the remarkable truth emerges clear and irrefutable. Revolutionary change often originates from those on the front lines. The workers whose eye for detail and instinct for pattern recognition uncover truths the textbooks might miss. Hamill's story reminds us that innovation isn't solely born in university labs or corporate boardrooms. It is often born in the gritty reality of daily toil, where observation and experience combine to challenge assumptions and forge progress. The question then hangs in the air: how many other hidden insights, unnoticed by the mainstream, are waiting to reshape industries? How many future breakthroughs are lurking in the most unexpected corners of human effort? The answer is as inspiring as it is humbling, because the lesson from Hamill's story, her unrecognized but transformative insight, is that progress often arises where least expected. It reminds us that frontline workers, with their keen observations and unwavering dedication, can and do become the unseen catalysts of revolutionary change. Change that saves lives, shapes industries, and leaves an indelible mark on history. Their stories, often unspoken, are the true engines of progress, the quiet, relentless force that propels humanity forward.